derivative. So this is 3 dy by dy minus derivative of c squared by dy. So it would be just 3 times 1 and then minus 0. So we conclude that df by dy will be, this is just 3, right? So minus 3x, and then, oh, I'm sorry, I should say psi, I'm sorry. And it becomes sine of 3x minus, I'm sorry, 3y. Okay, with the same function. And then lastly, we do df by dz. It would be d by dz of x times cosine 3y minus c squared. Here x and y are constant. So first of all, we take x out of the derivative side. So the rest would be cosine of 3y minus c squared. This time, we let y to be constant, so this is just some constant minus c squared. So this is function of z. Cosine of function of c, when we find derivative, we need to apply the chain rule. So that come out to be the same as the previous case. We get minus sine u. And then d by dz of 3y minus c squared. Minus x times sine of 3y minus c squared. So the derivative of 3y minus c squared, the first one, derivative of 3y becomes 0, and derivative of c squared becomes 2z. And this is minus 2z, and this is minus, so it becomes plus. So it becomes 2xz, and then sine 3y minus c squared. And that is how we can get the partial derivative of the 3-variable function. Okay? Remember, to find the df by dy, x and z are constant. Okay, so we take it out. Do df by dz, x and y are constant, so we can take x out. That is the way we can find the partial derivative of the function of more than 2 variables. And this idea can be extended to the case of the function of any n variable. We find partial derivative with respect to one variable. You need to keep another n minus 1 variable to be constant. Okay, and this idea can be done in the case of 4 variable or 5 variable functions. Okay, now let's move on to the next topic. The next topic is about the higher order partial derivative. In the case of one variable, when you find the derivative of a function and you apply the derivative one more time, then it comes out to be the second order derivative, right? Now, let's consider the case of partial derivative. When we do the partial derivative, we can do the second order partial derivative in the same way. But since in the case of function of two variables, there are two forms of derivative of one of the first order. So since we have df by dx and df by dy as the second order derivative, right? And where we have two choices to apply. So for df by dx, we can apply the derivative in two ways. Namely, we can do d by dx or we can do d by dy of the derivative with respect to x. And similarly, when we have the derivative with respect to y, we can apply the derivative with respect to x of this function. And we can do d by dy to this function. So we conclude that for the case of the function of two variables, there will be four types. There will be four types of the second order partial derivative. Okay, because we have two first order partial derivative, and we have another two choice to apply another derivative to it. So there are 2 times 2 become 4 form of the partial derivative. Okay, so I hope you understand the meaning of this. We differentiate to x first and differentiate to x at the second time. For this one, we differentiate with respect to y first and then apply the derivative with respect to x to it. This one, we find partial derivative with respect to x first and partial derivative with respect to y later. There are 4 forms of partial derivative. Now, let me talk about the notation for that. The first one, this is we write down the notation d square. That means it would be the second order derivative of f. And this is dx and dx we write down as similarly as when we do the ordinary derivative. Now for this one, we're gonna use, let me write it in this way because we have less space there. Here again d square f. This is tell us that this is the second order derivative of f. And when this is, we write down dx dy. So we just say dx dy. And similarly, this one would be dy dx. And lastly, this is, we do the same as the first case, so this is dy square. And this is the notation for the second order partial derivative. There are 4 types of second order partial derivative of the function of two variables. Okay, so whenever you see this notation, try to write down it in this term. Try to write down term so that you know which variable that we need to first find the derivative of the first order. Like this case, d square f by dx dy. That means we need to do df by dy first, and then apply d by dx one more time to the partial derivative with respect to y. So this is the meaning of the notation. And what about if we want to do the subscript notation? Since there are 2 forms of partial derivative, so we have subscript notation there. And if we do derivative with respect to x one more time, but this one we do with respect to y. Now let's see the notation here. This is fxx, this is fx and y, this is fyx, and this is fyy. So the notation would be this. So we write it in this order. That is the subscript notation for the second order partial derivative. Okay, so whenever we have seen fyx, that means fy is inside, and then we do derivative respect to x later. So from this idea, that means d square f by dx square here, it would be fxx. D square f by dy square here, it would be fyy. But now look at this. D square f by dx dy, it would be, this is df by dy first, right? It would be fyx. So this is something we need to be careful. This is exactly the same thing. D square f by dx dy, that means we differentiate y first and x later. But when we use subscript notation, that means fy and then x, so it becomes fyx. So here is yx, here is dx dy. That is what I want you to focus on. Okay, so when we use a denotation, the order derivative comes from right to left. That means we do dy first and then dx later. But when we do subscript notation, we need to differentiate with y first and x later. So the order would be from left to right. Okay, so that is the reason why here this is dx dy, but this is yx. Okay, understand? Try not to get confused with that. X dy is f, not fxy. Remember, dx dy is fyx, not fxy. So dy dx here should be fxy. It means differentiate with x first and y later. But for this one, with respect to x first and y later, so it comes from left to right. Okay, so for this two would be no problem because it's the same variable. But between x and y, the order would be important. It would be different meaning. Okay, it has different. Now let's look at some example here. Okay, so in this example, the function is given. Remember that. For this given function, we have found df by dx and df by dy before. Can I write down it somewhere here? Here df by dx. I'm just thinking where should I write it? df by dx. If you remember, we have done this before. It becomes 3x squared. And this one, we differentiate xy become 2x, so this becomes minus 6xy. And for this one, it would be plus 3y squared. Plus 3x squared of df by dx. And so we can just apply d by dx. There. So you can differentiate it quickly, right? Can you do that? 3x squared by dx, that would be 3 times 2x. Okay. And then next one, we take 6y out, and dx by dx would be 1. And lastly, that would be 0, because what 3y squared is constant with respect to x. Now for this one, this is d by dy of what? Of df by dy. So we just one down. So this result become minus 3. Oh, sorry. Minus 3x squared is constant, so it becomes 0. The next step, we take 6x out, and dy by dy become 1. And lastly, minus 3 out, and derivative of y squared become 2y. So this becomes 6x minus 6y. Oh, it's just coincident that they are equal. Now, for this notation, this one should be d by dx as the outer. And then okay, so please make sure you do it in the correct order. That would be d by dx of minus 3x squared plus 6xy minus 3y squared. So the first term, we take minus 3 out, derivative of x squared becomes 2x. The next one, we do d by dx, so 6y is the constant, and dx by dx would be just 1. And lastly, last term becomes 0. So that becomes minus 6x plus 6y d square f by dx dy. And the last one, d square f by dy dx, so this is d by dy of df by dx. And that would be 3x squared minus 6xy and then plus 3y squared. The first term is 0. The second term, we can take 6x out, dy by dy become 1. And lastly, derivative of y squared become 2y. So that becomes, again, minus 6x plus 6y. dy dx. So in this example, the functions are quite symmetric between x and y. That is why the second order derivative come out to be the same. And the mixed partial derivative come out to be the same as well. Okay. Is that correct? Any mistake? one? This one? No, the first term, df by dy here, the first term derivative of x cubed becomes 0. Maybe I need to put 0 there. And this is minus 3x squared, and dy by dy become 1. Okay, we have done this before. I just copied the solution of the previous solution here. Okay, understand now? Okay. Now let's look at the next example. Let's look at the next examples. So in the next example, the derivative is already given. But let me explain you a little bit more. Okay, for those who have finished noting it down, just look at the next page. This is a function we have found. This is the result that we have got. We have already got this one before. Okay, this is we have done before. Now, if we want to find the second order partial derivative of this function, there be 4 types of second order partial derivative. Now let's try to do each one. Okay. Okay, now let's look at the second order partial derivative. Let's do d square f by dx square and d square f by dy square first. D square f by dx square, that means we take the derivative with respect to x to the blue one here. You can see that since both of these contain x and y, right? Both of these contain x, so both the denominator and numerator contain x, so this is the quotient of two functions of x. Therefore, we use the quotient rule for that. And become v du. When we differentiate the numerator with respect to x, it becomes 0 minus 2x, and that is why minus 2x come out here. V du, right? And then minus what? Minus u dv, so minus this one. It comes out to be this u. And for dv, we differentiate the denominator here. It becomes 2 of x squared plus y squared. So this is 2 of x squared plus y squared. And then we differentiate x squared plus y squared with respect to x. We come out another 2x there. So this is v du minus u dv. And then divided by v squared. So this is to the power 2, and therefore when we take the square, it becomes 4. Okay? Now, d square f by dy square. This is df by dy. I'm sorry, d by dy of df by dy. So we do d by dy to this function. Again, this contains x and y, so we can think of this as the quotient of function of y. And we can use the quotient rule for that as well. So v, this one is v, and du. We differentiate minus 2xy with respect to y. So we take minus 2x out, dy by dy become 1. So that would be minus 2x there. V du, and then minus u, so minus u become minus 2xy there. And for dv, the result would be the same as the previous case, 2 of x squared plus y squared. But this time, when we differentiate x squared plus y squared, we got 0 plus 2y. So that is why we obtain 2y here. And then divided by v squared, and that would be x squared plus y squared to the power 4. Now, if you compare d squared f by dx squared and d squared f by dy squared, since the function here is not symmetric between x and y, so you can see that d squared f and d squared f by dx squared and d squared f by dy squared here come out to be different. When you compare it, you can see that this term come out to be the same, right? Clearly that this one is the same, but it would be different right here. So this one, it would be 2xy squared minus 2x cubed. That would be two terms subtract together. But this the whole the whole partial example they show, because the function is not symmetric, so it can be seen that d square f by dx square and d square f by dy square come out, they are not equal. But what I want you to focus on would be the mixed partial derivative. The mixed partial derivative. Okay, I would not expand it out. You can try to expand it out and show that they are not equal. Okay, but now, if you look at d square f by dx dy and d square f by dy dx, okay, even the way to find partial derivative come out to be in different order, but surprisingly, if you expand this out, you will see that they are equal. Okay, let me show you how to find the derivative first, and then we will expand it out later. Then look at this. The partial derivative of dx dy, that means we do d by dx to this rate function. To do d by dx of this rate function, again, this one is a quotient of x, so we apply the quotient rule. Okay, the first one, v, and when we do differentiate the numerator with respect to x, we take minus 2y out and dx become 1, so this is minus 2y. And then minus what? Minus v, minus u, so minus 2xy there, and then differentiate this one with respect to x. So we got 2 of x squared plus y squared here. And when we differentiate this with respect to x, it comes out to be 2x there. Okay? So it comes out to be this term. And for dy dx, that means we are doing d by dy to this function. We do d by dy to this function. Don't forget we do d by dy to the red one there. To the blue one there, I'm sorry. This one we do d by dx of the red. Okay. Now we do d by dy of the blue one. Again, we use the quotient rule v and then du. When we differentiate y squared minus x squared with respect to y, dy squared becomes 2y, dx squared becomes 0, because we do differentiate with respect to y. So this becomes plus 2y. Okay, and minus u y squared minus x squared there, and then dv. We differentiate this with respect to y. It becomes 2 of x squared plus y squared, and when we differentiate x squared plus y squared with respect to y, we get 2y there. Okay, now, so we have checked that this is correct. Now let's try to expand this out. Let me show you d square f by dx dy. Look at this, we have the x squared plus y squared, which is the common factor. Now, the rest would be minus 2y times x squared plus y squared. For this one, we take this one out already. We take this one out already. So we have minus 2 to minus 2 become plus 8. And this x become x squared. So plus 8x squared y. Okay, one term of this can be cancelled. No, I'm sorry, I mean 4. And so this come out to be 3. And we can just multiply this out. Minus 2x squared y minus 2y cubed, and then plus 8x squared y, and x squared plus y squared to the power 3. So we conclude that the square by dx dy 8x squared y minus 2x squared y becomes 6x squared y minus 2y cubed, and then divided by x squared plus y squared to the power 3. Now let me do another one. What about the square f by the y dx? Let's look at this one. Again, we can take x squared plus y squared out. This one would be 2y times x squared plus y squared. And this will be minus 4y. And then times y squared minus x squared. Okay, one term of this can be cancelled. Now expand this out. 2x squared y plus 2y cubed minus 4y cubed, and then minus 4 plus 4, I'm sorry, plus 4x squared y. 2x squared y plus 4x squared y becomes 6x squared y. Plus 2y cubed minus 4y cubed become minus 2y cubed. So by expand it out, even if we can do the partial derivative in the different order, but when we expand the result out, you can easily see that in this example, these two mixed derivatives come out to be the same. Okay, so these two is not equal. So in the previous example, it just coincident that they are equal. But for the case of the mixed partial derivative, so if you look at the original function, the function is not symmetric at all. But the mixed partial derivative come out to be equal again. Is this coincident? Is it coincident that they are equal? The answer is no. Now, the question is, do these two mixed partial derivatives always equal? That come out to be a big question. Because if they are always equal, that means the order is not important at all. We can do each variable first and another one later. It does not matter at all, right? If they are equal. Okay, if they are equal, then the order finding the partial derivative is unimportant. We can do dx first, or we can do dy first. It does not matter if they are equal. But unfortunately, the mixed partial derivative in general, they may not be equal in general. Okay, in general, they may not be equal. That means the order still be important. The order still be important. So you might wonder, and then why the given functions seem to be not symmetric and they give the equality of these two mixed derivatives. So there are a theorem guarantee the equality of the mixed derivative there. And that is what we call the mixed partial derivative theorem. Okay, so let's try to see. Okay, note that you can note it here. Let's write it down. Okay, let's try to find somewhere to write it down. That try to find the back color. Okay, here. Note that in general, d square f by dx dy and d square f by dy dx may not be equal. Okay, you cannot guarantee that A always equal. There is some function f that give different of the mixed partial derivative. Okay, in general they may not be equal. Okay, that means there is a function. There is a function f such that this fxy does not equal to fyx. I don't have some space, so let me change the notation a little bit. That means there is a function such that they are not equal. Okay, but in our example, our function would not be this function, so they are equal. Okay, so you might wonder how can we know which function that going to have the equality of this mixed partial derivative, right? So that can be guaranteed by the following theorem. Okay, it can guarantee the equality of the mixed partial derivative. That is called the mixed partial derivative theorem. Can I take this out? Okay, maybe if you want to note this down, just note it here. Okay, so in general, they might not be equal. And that is the reason why we need to find some theorem to guarantee the equality of the, the mixed partial derivative. Okay, note that the second order partial derivative, d square f by dx dy and the d square f by dy dx, these are called mixed partial derivative. These two are called mixed partial derivative. So the theorem guarantees the equality of fxy and fyx. Let's see the assumption of the theorem. The equality of this is the equality of xy and fxy, right? Now let's look at its assumption. What that is say? The assumption says that if your function f, okay, and its four partial derivative, two of them would be the first order, fx and fy, and fxy and fyx. So how many functions there? 5 functions. F, fx, fy, fxy, and fyx. If all of these 5 functions, all of 5 functions, which is f itself and its two first partial derivative and another two mixed partial derivative of second order there. If all of these 5 functions are defined in the open region containing AB, say AB can be just a point and we just look just the small neighborhood of this point AB. We have the point AB here and we just try to find a small neighborhood in the region of R2. The point AB is inside. And if all of the point xy in this small region, this function exists, are defined mean the function is defined where region the partial derivative exists in this open region, and this is important. And if they are all continuous, all of it are continuous, then the order is unimportant. Then the order of d by dx and d by dy does not matter. Okay, so in our case, let's look at in our case here. It can be shown that our function satisfy the condition of the mixed partial derivative theorem, so it guarantees the equality of this. But this one continuous everywhere except the point 0, 0 because the denominator would be 0. So this they are equal everywhere except the point 0, 0 because it is undefined. The function is undefined at that point. Now let's look at the next example. Okay, this is a mixed partial derivative theorem. Now for this one, the function is just simple as the cosine. So please note that 3x minus y squared is a polynomial of x and y. So it would be continuous everywhere on R2. X can be real number, y can be real number. 3x minus y squared always continuous at any point x, y in R2. And the cosine would be a continuous function. When we do the composite of them, the composite of two continuous functions would be continuous. So this function is continuous at all points, at everywhere. In fact, at all points x, y in R2. And when you find it, the f by dy and the mixed derivative, when you all can do the derivative, right? So this one, df by dx is given to be this. Again, 3x minus y squared is continuous. And when we do the composition it with the sine function, this is still be continuous. So this function is still continuous everywhere. Even df by dy, this is the composite between sine function and this. And when we do multiply with the y function, this is also continuous. That means all of these 5 functions would be continuous. All of these 5 functions would be continuous. And by mixed partial derivative theorem, we can guarantee that the mixed derivative would be equal. Okay, so for actually what I want you to focus on here is that most of the functions we learn in calculus, most of them are nice function. Most of them are nice, and most of the example you have learned in this course, usually the derivative, the partial derivative, the mixed partial derivative are equal. Okay, that would be one of the very complicated examples to show that the mixed partial derivative they are not equal. That example are would be very strange function that the big partial derivative are not equal. So if you are interested, you can try to search from the Google. The form of the function seems to be very complicated, and I also cannot remember how it is defined. Okay, and I do not include that example in this note. So if you are interested, you can try to search from the Google. Just try to search like an example of the function that mixed partial derivative are not equal, for example. Okay, try to see how the function is defined. As of now, I could not remember as well. It would be a complicated one. Okay? But another thing is, remember that in the exam, if I ask you to find one of the partial derivative, please try to do it in the correct order. Because even if your answer come out to be the correct answer, but if your method doing that is incorrect, then your score will be deducted, remember. Okay? Try to do it in the correct order then. Even if the answer is acceptable, but the method is also important. Okay, to get full points, you need to do it in the correct order. Okay, now let's move on to, now for the case of higher order, order 3, the third order, the fourth order derivative, it can be defined the notation in the same way. Okay, so for the third order derivative, like the cube f by dy dx, this one it means d by dy of d square f by dx square. And d square f by dx square would be what? It would be d by dx of df by dx. That means when we need to find d by dx first, and then find the derivative with respect to x one more time. And lastly, we do d by dy. And if you want to write this in terms of subscript notation, we do fx first, and then we do fx, we do x one more time, and then y. So when we do fx, and then x, and then y, so this is f. Okay, so this is x, this is x. Okay, the notation would be the same. So this one, the fourth y by dy squared dx squared, that means df by dx, df by dx, d by dy, d by df x. So this one would be d by dy by dy, d dx. X, and then y. And by the notation here is fx, x, and then y, and then y. And that would be f, x, y, y. Okay, so the notation can be defined in the same way. So here, if in this example, they want you to find the cube f by dy dx squared. What you have to do, we need to differentiate with respect to x first. Just write down this notation as d by dy, d by dx of df by dx, and then begin with this one first, df by dx. This one we have found it before, in fact. Okay, so it becomes minus sine 3x of y square minus y square, and then differentiate 3x with respect to x. So it becomes 3 minus 0. So that becomes minus 3. And once we have df by dx, then we need to find d square f by dx square, which is d by dx of df by dx. Okay, so we just differentiate this one with respect to x. The derivative of sine u become cosine u, and then derivative 3x minus y squared become another 3, so this is minus 9 cosine. And lastly, once we have d square f by dx squared, we do d by dy one more time. So that would be d by dy of d square f by dx squared. And that means we differentiate this with respect to y. So it becomes minus 9. The derivative of cosine becomes sine u. And the derivative of 3x minus y squared with respect to y becomes 0 minus 2y. So we get another minus 2y there. And finally, this becomes 9 and minus 2y become minus 18y. And then the sign. Okay, for the higher order, just try to do it step by step. Okay, write down the once we write down the notation, you need to rewrite it in terms of this and then start with the inner one and then move on from right to left. But for the subscript notation, you do it from the inner one to out. That would be from left to right. Okay? Now this is the higher order derivative for order 3, order 4, and so on. Okay, that next one, again, if you remember in one variable, there is a theorem say that if f is differentiable at x0, then f is continuous at x0. I hope you still remember this. i.e. f prime of x0 exists. F is con at x0. And please note that the converse is not true. Everyone has seen this before. Namely, when f is continuous at a point, f prime of x0 may not exist. So the converse may not be true. One of the examples that you can remember zero. Is delta x minus f0. And that would be the limit delta x go to 0. You can see that the left limit here go to plus 1 and the right limit here go to minus 1. So the left limit and the right limit are not equal. As you can see, the left limit here, the slope of the tangent line at any point on the left, the slope would be minus 1. And the right hand limit, the slope on the right hand side become plus 1. So the slope of the left hand side and the slope of the right hand side come out to be minus 1 and 1. That means the left hand limit and right hand limit may not be equal. Okay, so f is not differentiable. This one is a result of one variable. Now, this theorem can be extended to the case of 2 variables and 3 variables and so on. Okay. In the case of 2 variables. Differentiable at x0 when the derivative exists. be two variable. The function of two variable is said to be differentiable. Be differentiable both of these. Okay, if either one of these does, then it's differentiable. To be differentiable, all of partial derivative must exist. All of partial derivative at each independent variable must exist. Namely, for the case of three variable, if you have the function of three variable, it's said to be differentiable if all